Good afternoon to all of you. Today we are going to have a lecture on micro remote sensing for archaeological applications. Here we will be talking about space-based and the ground-based systems. Here I would like to show the appearance of a cultural heritage site in SAR imagery. When we are talking about the SAR data sets, so SAR data sets are not sensitive to the color information. They are mainly sensitive to the structural and electrical properties of the targeted object. So if the surface is smooth, so very less scattering will occur, and finally surface is going to appear as dark because very less scattering will be there, and there will be complete reflection, or the maximum energy which will be transmitted by the SAR sensor will be reflected away from the direction of the sensor, so that those kind of objects are going to appear as a dark object. Like here, if you see, this is the Angkor area, and this is the water body which is surrounding the Angkor area. So here we can easily see that this water body is appearing very dark. And if you will see the Angkor temple area, the main temple area. So if you see this temple area, so in this temple we can see that the temple is appearing relatively brighter. Why? Because the man-made structures are going to appear as very dark feature, because there will be a kind of double bounce scattering that will contribute due to the surface as well as the building. So those kind of objects are going to appear relatively brighter. So here in all the imageries, here I have included the X-band and L-band SAR sensors. So here you can see that the first image is of TerraSAR X-band dataset. So in this X-band dataset, we are able to see the temple area, and we are able to see the water body clearly, and even we are able to see clearly the walls, different walls, because the main temple is having the several layers of walls. So those walls could also be seen clearly. And similarly in the TandemX dataset, because both are having the similar resolution, TerraSAR X and TandemX, particularly for this image, they both are having the same resolution. Now when we are coming to the LOS1 and LOS1 Pulsar 1 and LOS2 Pulsar 2, this is the L-band SAR dataset. So in L-band SAR dataset, and the resolution is, spatial resolution is relatively coarser. So here we are not able to see the exact shape and size of the building because the resolution is coarser. But here all the other features like water body and the vegetation scattering from vegetation could be easily seen. Now here, since this is a high resolution data set, so here if you see carefully, the canopies could also be counted. We can also count the number of trees based on the canopy cover. So from here we can get the several information, because here spatial resolution is high. Now, why we are using SAR dataset? So we will be discussing more on that also. But here I am going to show you a comparison between optical dataset and the SAR dataset. So left-hand side image is a polydecomposition image, which is generated with the help of the 4 polarimetry combinations HH, HV, and VH and VB. So polydecomposition image is generated, and this is the Google Earth image of the same area. So here if you see the in the Google Earth image, so this is the true color composite image. So this area, particularly if you see, particularly this area, the upper portion, so this is appearing very smooth. But in the SAR dataset, if you see in the SAR dataset, so this is clearly visible that like the surface which is appearing as smooth in optical dataset is actually not very smooth, because there is subsurface penetration of the electromagnetic waves which is used by the SAR sensor. And here, due to the subsurface penetration, we are able to see the subsurface features. So like here paleo channels, and these channels could be easily seen. So SAR data set is widely used, particularly microwaves are widely used to retrieve the subsurface information. It has very wide applicability in the archaeological feature detection. Now, I have shown you few images of synthetic aperture radar. So before starting the direct applications, we should have some basics of the synthetic aperture radar remote sensing. So synthetic aperture radar is a form of radar that is used to create images of objects such as landscapes. These images can be either 2 or 3-dimensional representation of the object. Now, synthetic aperture radar remote sensing is type of microwave remote sensing. So, microwave remote sensing is the remote sensing which is carried out in the microwave region of the electromagnetic spectrum. And this microwave region of electromagnetic spectrum is having the wavelength ranges from 1 millimeter to 100 centimeter. And synthetic aperture radar remote sensing is an imaging active microwave remote sensing technique which provides higher spatial resolution. So we have already seen that higher to coarser spatial resolution data set, particularly for the Angkor area. Now this is the microwave band. So microwave band is covering basically from K band to P band. So here you can see that when you move from K band to P band, so the wavelength range is going to be increased. And but when the wavelength is increasing, so in the same way the frequency will be decreasing, because we know that the relation between the frequency and the wavelength both are inversely proportional to each other. It means that if one will be increasing, another will be decreasing. Now, for the archaeological purposes, generally we are preferring archaeological purposes, particularly when we are talking about the buried information retrieval or the ground penetration capability of the sensor. So at that time, we are preferring to use the long wavelength ranges data set like L band and P band. But to get the fine detail with high spatial resolution, so we can get the information from the high spatial resolution data set using X band SAR data set as well as the C band data also. Now, how the SAR sensors are operated to acquire the images. So here the radar geometry has been shown. So SAR sensor is placed here. This is an example of airborne SAR system. So SAR sensor is placed at the bottom of the aircraft, and this is flying in the forward direction. That direction is known as the azimuth direction. And all the SAR systems, they are not a nazi looking system. It means that they are not going to transmit the electromagnetic pulses in the vertical direction. All the SAR sensors will transmit the electromagnetic pulses either towards the left side or right side by making some angle to the nadir. So all the side looking radar systems are side looking radar systems, and they are going to transmit the electromagnetic pulses in a direction. That direction is known as a range direction. And there are several other parameters. There are several other terminologies like incidence angle and the depression angle. So incidence angle will be the angle between the incident electromagnetic wave and a normal down to the point of incidence. So the angle between the normal and the incident angle and the incident electromagnetic wave will be known as the angle of incidence. These are highly useful when we are talking about the ground penetration capability, because when the angle of incidence will be very large, then the ground penetration capability will be decreased, so that to get the high ground penetration capability, the angle of incidence should be very, very small. Now, there are different sensors like passive microwave sensors and active microwave sensor, because in microwave remote sensing, again, microwave remote sensing is categorized into category passive and active. So passive microwave sensor detects the naturally emitted microwave energy within its field of view. So the example is radiometer. So when we are having the word radiometer, it means that we are talking about the passive microwave sensor. There are different applications of passive micro remote sensing in meteorological, hydrological, and oceanographic application. And when we are coming to the active micro sensors, so in active micro remote sensing, again there are different type of sensors. imaging and non-imaging. So synthetic aperture radar remote sensing, which we are talking, this is kind of imaging sensor, which is going to provide you an image of the targeted study area. There are non-imaging sensors also. These non-imaging sensors are altimeter and spectrometers. And these sensors are also used to retrieve the information, like radar altimeter is used on an aircraft for the altitude determination. And it is also used for the topographic mapping and the sea surface height estimation. And spectrometers are generally non-imaging sensors and are used to make precise quantitative measurements of the amount of energy back scattered from the target. There are different applications of spectrometers also. Now, this is a comparison between SAR and the other Earth observation instruments. So when we are talking about the platform, so we have currently we have the two spaceborne LiDAR sensors. One is GDI and another is ISIT. So with the help of that, nowadays spaceborne is also possible. But most of the time, people are preferring to do the airborne LiDAR survey to get the high spatial resolution data set. Now, optical multispectral and SAR both could be operated on airborne as well as the spaceborne. Now, when we are coming to the radiation, so LiDAR and SAR both are an example of active remote sensing technique. They will have their own radiation. So they are not dependent on the sun illumination. So the imaging and mapping could be done in day and night, both the time period, because they are not dependent on the sun's illumination. They can generate their own electromagnetic wave. But the optical multispectral sensors, they are dependent on the reflected sunlight. So these could be operated mainly in the daytime. Now, when we are coming to the spectrum of the electromagnetic wave, which is used in doing the imaging, so generally in the LiDAR, infrared range of the electromagnetic spectrum is used. In optical multispectral, this is visible and infrared, and in the SAR, this is microwave. Now, when we are coming to the frequency, so frequency-wise, LiDAR can provide could be operated on single frequency. Optical multispectral will be operated on multi-frequency. And single SAR sensor is going to provide the data set in single frequency. But when we are going to use the multiple frequency data set by multiple sensors, so we can get the multi-frequency data set. Now, in archaeology, several people have explored these two techniques, polarimetry and interferometry, because currently polarimetry and interferometry is currently not possible with LiDAR-based system and optical multispectral sensors. And in the case of synthetic aperture radar, due to the long wavelength ranges, there is less effect and less disturbance due to the atmospheric particle, as well as the source of the electromagnetic wave is coherent and fully monochromatic. So at that time, polarimetric phase and interferometric phase both could be preserved and retrieved from the data set. And when we are coming to the acquisition time, so LiDAR and SAR both are active sensors, so both could be operated in day and night time, and optical multispectral is operated in daytime only. Now, when we are coming to the weather, so LiDAR and optical multispectral both are blocked by the cloud cover. So in the rainy season or cloud cover, when it will be completely blocked by the atmosphere, will be completely blocked by the clouds. At that time, these sensors are not going to provide the fruitful information of the Earth objects. At that time, only SAR sensor can provide the information of the Earth surface. Now, SAR imaging is done. Here, this has been shown through this representation here. So, SAR sensors are transmitting the polarized electromagnetic waves. So, here, horizontally polarized electromagnetic wave will be transmitted, and horizontally and vertically polarized electromagnetic waves will be received, so that the combination will become HV and VH. Now, in the case of vertical polarization, when the vertical polarization will be transmitted, so at the time of receiving, vertical and horizontal both will be received. So at that time, the combination VV and VH both will be received. So SAR sensor can provide the data set in four polarimetric channels, HH, HV, VH, and VV. Now here we are going to see the graphics which is generated by the European Space Agency. This is showing the imaging of the SAR sensor. So SAR sensor is transmitting electromagnetic pulses, and you can see that it can penetrate the cloud cover and it provide the information of the Earth surface. And based on that, interpretation could be done, because the dark objects, these are this is the water body, bright objects, very very bright, these are the urban settlements. And similarly, we are going to be doing the interpretation of the different objects. Now, when we are talking about the SAR data set, so SAR data consists of high resolution reflected returns of radar frequency energy from terrain that has been illuminated by a directed beam of pulses generated by the sensor. The radar returns from the terrain are mainly determined by the physical characteristic of the surface, as we have talked that the electromagnetic waves used in the SAR remote sensing are mainly dependent on the structural property, that is including here the surface roughness and geometric structure and the orientation, and it is depending on the electrical properties, so that is including the dielectric constant, moisture content, and the conductivity of the targeted object or the surface. So here you can see that this is the high resolution synthetic aperture radar data set for the Visakhapatnam area. So in this area, you can see that all the objects are appearing bright or dark according to their structural as well as electrical properties. Now, when we are going to do the mapping with the help of the SAR or ground penetrating radar system, so we should always have to keep in mind, this slide is going to show you, like when the soil will be dry. When the soil will be dry, so what will happen? The transmitted electromagnetic wave will have more penetration. So at that time, less scattering will occur, and the dry soil is going to appear as the darker object. And when we will see the wet soil, so in wet soil, when the wetness will be very, very high, there will be very less or no penetration, or due to the less penetration, the scattering will be more. So more return will be received by the sensor. So wet soil is going to appear a very, very bright object. And in the case of flood, we cannot get any penetration, because entire surface will be covered by the water body, and whatever the amount that will be transmitted by the sensor, entire amount will be reflected away from the direction of the sensor, because SAR waves cannot penetrate the water body. When water comes in the picture, microwaves or SAR waves are going to surrender. So here we will have to keep in mind, when we are going to talk about the subsurface information retrieval or the buried object information retrieval. So we will have to keep in mind that we will have to select those days or that season in which the soil is dry. Then only we can get some subsurface feature information. Now in synthetic aperture radar remote sensing, there are different techniques which are used. These are the polarimetric SAR, interferometric SAR, differential SAR. The advanced version of differential SAR is a small baseline as well as the persistent scatter SAR interferometry. And by combining the polarimetric SAR and interferometric SAR, there is technique the polarimetric SAR interferometry. Now there is another technique in the SAR, that is SAR tomography, which is used to generate the two-dimensional or three-dimensional representation of the object. With the help of SAR tomography, one will be able to generate the 3D view of the targeted object. Now, when we are coming to the synthetic aperture radar remote sensing, so here we are talking about the polarimetry. So in SAR polarimetry, we are going to deal with with all the four polarimetric combinations of the SAR data set. So maximum possible combinations are these four: HH, HV, VH, and VV, where HH is representing that horizontally polarized electromagnetic waves were transmitted and horizontally polarized electromagnetic waves were received, and in HV, horizontally was transmitted, vertically was received. Similarly for VH and VV. Now, why we are using the SAR polarimetry? Because when we will have the fully polarimetric SAR data set, so in a small area or within a resolution cell or within a pixel, if there are several kind of objects, suppose there is 50-meter resolution cell in which this surface scattering, because here you can see that single bounce scattering is there. SAR sensor is transmitting electromagnetic pulses, and all the electromagnetic pulses are going away from the direction of the sensor. So this is going to contribute in surface scattering or single bounce scattering. Another scattering is double bounce scattering. That is double bounce scattering is very common, mainly in the urban area, when there will be smooth surface, and in the nearby, if there will be vertical wall. So what will happen? Whatever the amount, it will be reflected by the smooth surface will be interacting with the vertical object or vertical wall, or if there is T, so it will be interacting with the tree stem, and entire amount will be reflected back towards the direction of the sensor, so that these kind of objects, double bound scatters, are going to appear as a very, very bright object in the SAR imagery. And this is volumetric scattering, either due to the subsurface penetration, if there are multiple kind of objects, so this volumetric scattering is obtained, or if there is vegetation canopy, so that is going to contribute in the volumetric scattering, because entire volume of the object is going to contribute in the scattering, so that this volumetric scattering will be high. And helix scattering is a special condition of volumetric scattering, where we are going to get if the shape will become the helical. So at that time, helix scattering will be obtained. So mainly these 3 to 4 type of scattering elements we are retrieving from the SAR data set, and they are having their unique scattering pattern, and we are doing the analysis based on that. And when we are coming to the interferometric SAR, so in interferometric SAR, we are going to use the concept of the SAR interferometry by the interference of the electromagnetic wave. So in this case, to do the interferometry, there is a requirement of the two SAR data sets with the same SAR geometric conditions. Both the images should be acquired by the same sensor in same SAR geometric configuration, like the same number of polarizations and same angle of incidence. So this data set will be suitable for the SAR interferometry. SAR interferometry has been widely used to generate the 3D view or to generate the digital elevation model. And SAR interferometry has also been used for the subsidence mapping and monitoring. So several SAR interferometry, particularly for the subsidence mapping and monitoring, has been widely used to do the subsidence mapping and monitoring of the archaeological sites also. Now, when we are coming to the differential SAR interferometry, so this technique was developed in 1989 by Gabriel et al. So this technique can provide the subsidence information or velocity information up to 1 centimeter. But by using the PSNSAR technique, one will be able to measure the subsidence on the ground surface at millimeter scale. So here in persistent scattering interferometry, a large number of images are required so that persistent scatter are identified on the ground, and their stability is identified, and accordingly the displacement is measured. Now, here we are going to talk about the SAR data analysis for one of the study site in Libya. So here you can see that this is the SAR data set, and this is the optical multispectral data sets which were acquired on August 2011 and May 2012. So here you can see that like in the SAR data set, this is a very famous archaeological site, but here several studies have been carried out, but here currently when in 2012 this site was unknown. So here you can see that the linear archaeological structures, if you will see the square shapes, these are clearly visible from the spacebound SAR data set, and these information are not very much clear in the optical multispectral data set. Why? Because SAR data set is having sensitivity towards the structural properties of the targeted object, so that they are in a systematic pattern, like this is the information on ground. They are not in very good condition, but here since they are in a systematic pattern, so we can easily see that like these structures are present in those areas, and you can see that this is done with the help of the high resolution, the Cosmos SkyMed X-band data set, and the other information is available in this research article. Now, not only the visualization, we can enhance the particular information with the help of the combinations of the SAR data set. Like this is normal intensity data, which has been given as a raw data. Basically, this is not in the terms of SAR remote sensing. This is not the SAR raw data, SAR intensity data, which is named as raw data. because this is showing that this is unprocessed. Now, after doing the processing, we are able to retrieve the several information, like when the sum of a square was implemented here. So here what we are getting that the boundary is enhanced, and when the filtering was implemented, so here we can see that the a kind of smoothing has been occurred, but the boundary information could be easily seen. Similarly, here you can see that this is the enhanced leaf filter of the image B. So here also we can see that a kind of smoothing is done, but then also we are able to identify the boundaries. Now this is one of the study site of the Sahara Desert. Here I have taken just to show the ground penetration capability. So here you can see this is this is Sahara Desert. So in the Sahara Desert, here you can see that the entire sands are appearing as gold in the golden color, golden yellow color. You can easily see. Just focus on the middle strip because this area is completely dry. When you are focusing on the middle strip, so what is happening? The electromagnetic waves are interacting with the subsurface feature, because microwaves are not only interacting with the surface since this is dry, so they are penetrating the surface and interacting with the subsurface. And here you can see that subsurface features, these are showing that these are the paleo channels. Paleo channels are there. So it gives a strong support to the observation or to the hypothesis which has been told that like Sahara was not a desert or not always a desert in past. So if the paleo channels are there, it means that when these channels were active, so it might be possible that there will be greenery also at that time in past. But currently, this is completely a desert area. Now, this is another image in which we are going to talk about the surface penetration capability of the SAR dataset. So here you can see that this is optical multispectral dataset, and here also you can see that this is optical multispectral dataset. This is the area of the southern Egypt, and here you can see that the surface is appearing very smooth. But when the same area was imaged with the help of the SAR dataset, so here you can see that there is complete penetration, and here you are able to see the paleo channels. Paleo channels could be easily seen here. This clearly shows the subsurface penetration capability of the SAR dataset. Similarly, this is based on the L-band and the airborne data set. So here also we are going to get the more subsurface penetration capability, which is not visible in the optical multispectral data set, but in the SAR data set, this information is clearly visible. Now, not only the single polarization, one can use the different polarimetric combination. Like here, if you will see the non-surface scattering regions, which include the subsurface scattering caused by the buried paleo soils, should appear in both HH and HV polarization, that they should have a higher HV and HH ratio and correspond to a lower HH minus BB correlation. So these are shown here. And this is the southern part of the study area, and this is showing the HH and HB polarization. So here we can see that in all the combinations, in all the polarizations and the polarimetric combination, we are going to get a different kind of information. Like here, particularly if you see this area is not enhanced in the image A, B, and C, but in the image D, this has been enhanced. So we are using the different combinations of the images so that we can get our desired information according to the need. And detailed information could be obtained in the IEEE TGRS paper of this article. Now, SAR interferometry, we are already knowing that there is a requirement of the two images. And with the help of the SAR interferometry, you can you will be able to generate the digital elevation model 3D map of the study area. Like with the help of the SAR interferometric data set, the interferogram has been generated from Fujian. The 3D view of the DM, which is generated from the same interferogram. And this is representing the overlapping of the Landsat TM dataset over the DEM. So we can clearly see the undulation in the terrain with the help of the digital elevation model, which is generated by the SAR dataset. Now, this is another image. This is the 3D surface view, which is generated for the Doon Valley with the same LOS pulsar dataset. Now we are going to talk about something related to the subsidence mapping and monitoring of the Angkor Wat study area that is in Cambodia. Now we are knowing that the Angkor Wat, this is the biggest religious place in the world, and this is also a UNESCO World Cultural Heritage Site. And the Angkor Wat was built by the Khmer king Suryavarman II during 12th century. Why this temple is important? Because this temple keeps several pieces of cultural information, including the details of four major time periods of the Hindu cosmology. Like we are knowing that there are four cosmological periods of Hindu cosmology, and these are the Treta Yuga, Satyuga, Dwapar, and Kali Yuga. So, if you will see that Dr. Stencil in his article of 1976, and some information you can get on my article also. I took the information from there. So for the different distances, they have measured that this much distance is representing this much year of the Dwapar Yuga, this much distance is representing the this much years of the Treta Yuga. So all the distances they are having the different time periods of the Hindu cosmology. And the addition of the exterior axis of the upper elevation represents the solar cycle of the Earth that is coming approximately 365 Hath. So 365 Hath is representing the solar cycle of the Earth. And there are several other solar and the lunar symbolism which were recorded in this temple campus. And in 1992, UNESCO declared this as a World Heritage Site. And here you can see that this is this is the temple area. The graphics has been taken from a book, and here you can see that the different towers of the temple and different layers, wall layers. You can easily see that there are mainly three layers. This is the outer layer, this is the medium layer, and this is the innermost layer. So all these layers are there. And this is the DEM based digital elevation, sorry, not digital, LIDAR based digital elevation 3D view of the entire area. And several people, this is one of the most studied site of the UNESCO. Why? Because several people, they are doing several kind of research, like people from astronomy and astrophysics. They are interested in doing trying to understand like the ancient Indian cosmological symbols which are there in the present in the temple area, and the people from the history and people who are working with the appearance and appearance of different time periods of the different civilizations. So they are also very much surprised, like what happened to this area, like this civilization is differently. By seeing the temple campus, one can see that this civilization were well developed and very advanced civilization. And what had happened to this civilization? Because suddenly entire area we are not getting any clue of this temple for the several hundred years, and suddenly people discovered this area, and this is surrounded by the forest. So people are interested to know that what happened to this civilization. So like something happened with the civilization, so that the civilization was completely lost. So that people are interested in knowing that also. And since this is having lots of cultural heritage information, so that UNESCO as well as the other researchers, they are also worried because this structure is very very old. If anything happen, if anything will happen with the temple, so it might be possible that suppose there is subsidence rate is very high. So if the subsidence rate will be very high, so it might be possible that that subsidence will be causing the causing on the ground, and entire campus or entire structure may be collapsed. So that the people are doing the timely mapping and monitoring of this area using different data sets, using ground observation, using spaceborne observation. People from geology, they are also doing the geological studies of this study area. And here you can see that this is the map. I took it from the tourismcambodia.com. And here you can see that not only the Angkor Wat, all the entire area is having the different temples which are dedicated to different Hindu gods. And this is a aerial view of the temple, in which we can clearly see the different towers, 5 towers of the temple. There are several other towers also which are buried, and like they are evacuated, or they are and evacuation is undergone also. Here you can see that those towers, main towers, are clearly visible. And I would like to show like what this is the 2D structural view of the Angkor Wat site. So if you will see the site number one, the site number one, this site, this is showing why, because several research work were carried out, so that they concluded that this area belongs to the Hindu civilization. Why? Because of Hindu and as well as the Indian civilization. Because here one side, side number one, this is representing the battle of Kurukshetra. Side number two is representing the Suryavarman army, Suryavarman second army. He was the king who built this the temple. Side number three is Heaven and Hell Gallery. And side number four is representing the churning of the ocean milk, and that is also known as the Amrit also, Amrit Manthan. In Hindi, this is very famous, Sagar Manthan and Amrit Manthan. Okay, so this is very famous. And side number five is showing that the sculptures of the Vishnu, Lord Vishnu conquered demons. And side number six represents the Lord Vishnu's victory over the Bana. And sign number seven shows the battle of gods, and sign number eight shows the battle of Lanka, that is very famous in our culture, Indian culture, that is also known as the battle of Ramayana. So these details, some details, and this detail you can get in this book chapter. The book chapter is written by Kanda Swami and me, SAR for Cultural Heritage Monitoring, in the book of Spaceborne Synthetic Aperture Remote Sensing Techniques and Applications. Now, when we implemented the persistent SAR interferometry, because what is happening like this area is having is facing very huge tourism. So like several lakh of tourists, they are visiting this place every year. So what is happening? So the requirement of any tourist will be the from the hotel industry, it will be the water. So when the water will be pumped out, so there may be possibility of the aquifer compaction, and due to that aquifer compaction, that will be resulted at subsidence on the earth surface. And if there will be any subsidence in this area, because due to the heavy tourism and due to the heavy extraction of the pumping out the water, underground water. So what will happen in this area if there will be any effect? So since the structure is very old, so it might be possible that this will be collapsed. But here, when we did the mapping and monitoring with the help of the LOS2 and LOS1 data set, so we found that there is no subsidence and this area is stable. The region may be like this area is surrounded by this water body. So even if there will be any kind of like underground lack of underground water. So it might be possible that will be fulfilled by this water body. But anyhow, like there is no kind of water problem, especially underground water or the aquifer compaction problem, particularly in the location that we had detected with the help of the persistent SAR interferometry. In the persistent SAR interferometry, we had implemented the algorithm and with the help of that, we are able to find out the displacement also. So this displacement was approximately 0. Now, similar kind of study was also done previously by the several other researchers also, like one of the study which is carried for the Summer Palace in China. So in Summer Palace, China, when the study was carried, so this was the methodology of the study in which the SAR data sets were required and they were calibrated and co-registered, and persistent scatter as well as the distributed scatter were identified, and finally the deformation was measured. So this is the Summer Palace area deformation map. So here we found that the deformation is there, and that is the rate is approximately, subsidence rate is approximately 6 millimeter per year. So that rate was also detected. Now, the one study was also carried by Lee T.S. Chang, in which they did the subsidence mapping, land subsidence mapping for the historical center of Hanoi, Vietnam. So there also they had detected the subsidence. So here subsidence is mainly the high rate of subsidence is detected in the red color. So here you can see the red color is showing the high subsidence rate. And so here you can see that we have seen that with the help of the time series PSNSR mapping or the SBAS mapping, one will be able to find out the subsidence of any archaeological site. Now, due to this is the damage extraction of the heritage site in the Kathmandu Valley. So here you can see that the detailed information is available in the research article of the Fumio Yamazaki et al. So in this research article here you can see that the damage was clearly identified with the help of the SAR data set. So this damage was clearly identified. This is the normal condition when there was no damage, and when the due to this earthquake, here we are able to see that the damage occurred, and finally that was detected with the help of the SAR data set also. Now we have seen the several studies on the cultural heritage site, and there are several studies on the natural heritage sites also. Like this is the Galapagos Archipelago, that is the UNESCO World Natural Heritage Site. So here several volcanic activities are going on. So here one can do the volcanic mapping and monitoring also for this area. So here mainly we focused on the La Cumbre volcano, but we did the mapping for the entire area. So Fernanda La Cumbre volcano is this one. So when the SAR interferometry was done, so here you can see that the interferogram could be easily seen based on the change in the phases of the interferogram or interferometric phases. And you can see that there are several islands in this archipelago. And when we did mapping of with the help of the SBAS, so here you can see that particularly when there was volcanic eruption, so here you can see that the changes are occurring, and you can see that the changes are occurring, as well as you can find out the subsidence rate for the different region or different location. So with the help of the SAR interferometry, we can do the mapping and monitoring of the subsidence also. Now we are coming to the GPR. This is one of the widely used device to find out the buried information. So here we are going to have something related to GPR. So ground penetrating radar is a tool archaeologists are using more and more for excavation in the 21st century. GPR allows archaeologists to survey archaeological sites in the short amount of time with precision and without digging. Because here you can see that the GPR is placed and this GPR will transmit the electromagnetic pulses toward the here because this is near to the Earth's surface, so this will transmit the electromagnetic pulses, and those pulses will be received by the sensor. And based on the interpretation of those pulses, one will be able to find out the subsurface feature information. So this uses the radio waves to create the picture of the underground before excavation, and picture is used to locate any variation in the subsurface feature. And here electromagnetic waves emitted into the ground and time measured for the wave to be reflected and received. And when wave hits areas of change in soil, it is hit back to the receiver antenna, and change in soil can include the objects buried underneath the surface. Now here we are going to talk in the terms of, because the penetration capability is depending on several factors. But if everything will be the typical or the ideal situation, at that time 100 megahertz is going to penetrate up to 4 to 25 meter. 300 megahertz is going to provide penetrate up to 1 to 10 meter. 400 megahertz is going to penetrate 0.5 to 4 meter. 500 0.5 to 3.5 meter. 900 megahertz is going to penetrate up to 0 to 1 meter. So here what we are going to see, that higher the frequency, lower will be the penetration depth. When the frequency is small, like 100 megahertz, at that time penetration depth will be very, very high. But when we are talking about in the terms of resolution, so resolution will be very, very high in the low wavelength data set or high frequency data set. So one should select the GPR, the optimal frequency range for the GPR according to their applications. Like this is the GPR survey of one of the areas. Now here you can see that when the penetration depth is increasing, so more clarity could be seen here, because long wavelength ranges are used, so that more penetration is there, and we are able to see the clear picture of the buried object. So here and accordingly, the archaeologist can plan for this study area. Now I have covered my lecture, and I will be happy to answer your questions and queries.